But if I click on view, I see two buttons: close manage participants and close chat, nothing else.
Let me see. If I click on the black view options next to the green one, I see feed to window, different zooms, request, remote control, and annotate.
Ah, the view options, I see.
Yes.
View options, okay. Annotate, yeah. So I make this annotate.
Click on annotate, then click on the text, this capital T.
Yeah. And
then
I
click on the slide, just write something and enter. Not enter, just click outside the box, the text box.
Okay. Yeah, so can you see I have written 3 A's?
Yes, I see it. Then if you leave it, I don't think it goes away from its own. You have to click clear and clear my drawings.
Clear my drawings. So clear my drawings. Okay.
Well, you can clear all. You're the chair.
Okay. So
and then you have to close this bar with a red X button. Otherwise, you will keep writing on the slide every time you click. So you have to close that bar.
Okay, so each time I want to write on the slide, I have to open that bar.
You do the same thing every time, yes.
Okay, thank you. Okay, so welcome to the next spin session. And we have 6 very interesting talks in this session. Each talk is of 15 minutes plus 3 minutes duration, 3 minutes discussion time. And I would request all speakers to kindly stick to the time schedule. And I will give a warning at the end of 12 minutes. So the first speaker of this session is Minho Kim.
Yes, hello, can you hear my voice?
Yes, we can see your slides and we can hear your voice, so please start.
Yeah. Oh, yes, thank you. Hello, my name is Minho Kim from Korea University and Riken. I will present a measurement of the A sub n for manifold piezo production and 510 GB polarized proton-proton collisions. The name of our experiment is LIG-F. We measured the manifold piezo star with a new electromagnetic calorimeter. As it was well explained by previous speakers, the A sub n is defined as a left-right cross-section asymmetry of a specific particle or event. About the piezo, though the non-zero A sub n of it has been intensively studied for longer than 30 years, its relation to the proton spin is not completely understood yet. In this talk, I will discuss this issue from the viewpoint of the diffractive and non-diffractive processes. If we start from the non-diffractive process first, usually it describes the proton-proton collisions as a hard scattering between quarks and gluons. Since the scattered parton has a net chiral charge, a lot of parton productions are followed to compensate it, so their fragmenting hadrons finally fills the whole eta-fine plane up, as shown in right figure. About 75% of inelastic collision at leak energy is expected to be the non-diffractive process. If the measured π0 has larger than 1 g/c momentum, we consider it comes from this process and there is usually many particles around it. In contrast to the non-diffractive process, chiral neutral exchange between two protons is a characteristic of the diffractive process. So the particle production is suppressed compared to the non-diffractive one, and experimentally, a rapidity gap is observed as shown in right figure. Since higher order of partonic interaction is not suppressed in this process, the proton-proton collision is usually described as soft scattering using the mesonic degree of freedom. About 25% of inelastic collision at Lick energy is expected to be the diffractive process. If the measured pi0 has smaller than 1 GeV per C momentum, we consider it comes from diffractive process and it is usually isolated with a few particles around it. Then moving on to the experimental measurements, this figure shows the pi0 A sub n as a function of xf measured by previous experiments. So far, the non-zero A sub n has been observed by only the fold pi0 production, whose pseudo-rapid range is between 2 and 4. Since the momentum of the measured pi0 is larger than 1 GeV per C, it has been interpreted based only on the Cox and gluons degrees of freedom theoretically. For example, the non-zero A sub n has been explained to come from an asymmetry of the fragmentation process and spin-dependent quark-gluon correlations in the initial proton. However, a new question rose to the role of the diffractive process from an analysis result by star collaboration. As it was shown by Zhang Wenju speaker with the recent result yesterday, the issue is that the pi0 momentum is larger than 1 GeV per C, but larger A sub n was observed by more isolated pi0 than less isolated one. This figure shows the pi0 A sub n as a function of its energy measured by an electromagnetic calorimeter. From blue to red, pi0 is more isolated, expecting few particles around it. Actually, in this analysis, the word isolated means the pi0 energy fraction to the electromagnetic particles in this detector is close to 1. This definition is not connected directly to the diffractive process, but larger A sub n in more isolated pi0 still gives us a possibility that diffractive process may have a finite contribution to the pi0 A sub n as well as non-diffractive one. And this possibility was one of the motivations for the LIG-F experiment. This figure shows fold pi0 A sub n as a function of PT measured by previous experiments. And this region is the PT coverage where the LIG-F experiment measured. There has been no detailed measurement ever for the PT smaller than 1 GeV per C. In order to study the role of the diffractive process, in June 2017, we measured A sub n for very forward pi0 production, including other neutral particles. This page shows the experimental setup of the LIG-F experiment. Top figure is a simple view of the star experiment. If you see the most right side, there is a hadronic calorimeter GDC 18 meters away from the beam interaction point. We installed a new electromagnetic calorimeter, LIG-F detector, here in front of the GDC. As shown in left bottom figure here, the LIG-F detector consists of small and large sampling towers. If you see here, by moving detector, we measured the very fold neutral particles, including pi0, over the XF range from 0.2 to 1 and PT range from 0 to 1 GeV per C. Let me briefly mention the data taking and operation of the LIG-F experiment. We measured the pi0 by 2 ways. First, we have 16 GSO plates for both small and large towers, as shown here. This is a kind of longitudinal structure of the detector. If 2 decayed photons hit each tower as above picture, I would call this event as type 1. As shown in this orange field plate, this event is measured by so-called type 1 pi0 trigger, when the energy deposits of any three successive layers of both small and large tower are larger than 45 MeV. If the two photons hit a large tower together as below picture, it is measured by so-called high EM trigger when the energy deposit of the fourth layer of small or large tower is larger than 500 MeV. LIG-F experiment was operated during 4 fields for 28 hours. This figure shows beam intensity over time in 3 days during the operation. For the experiment, we requested several special settings. First is 90-degree rotated radial polarization. If you see the right bottom figure here, as it was presented, we moved the detector up and down for the wide PT coverage. For this geometry, if we use the usual vertical polarization, the measured asymmetry will be seriously diluted because most of the pi-zero azimuthal angle will be close to zero. So we used the 90-degree rotated radial polarization to measure the left-right asymmetry more easily. We also requested higher beta star and lower luminosity to avoid the multiple collision and decrease the additional systematic uncertainty by the beam emittance. Then this page shows the result of the varifold pi-zero A sub n as a function of xf in different PT ranges, which is different colors. The gray field width roughly shows the energy resolution of pi-zero, which is about 3%. Surprisingly, large pi-zero A sub n was also observed in varifold kinematic region where the diffractive process is expected to be dominant. If we see the data points from lower to higher PT ranges, a very low PT smaller than 0.07 GeV per C, the A sub n is consistent with zero. However, the higher PT range the A sub n is measured in, the more clearly it increases as a function of xf. Let's compare our result with the previous measurements. Colored data points are varifold pi-zero A sub n, and black ones are fold ones. Very interestingly, the magnitude of the varifold pi-zero A sub n seems to be comparable with the fold one, even at low PT smaller than 1 GeV per C. This again shows the possibility that non-zero A sub n of pi-zero may come from not only the non-diffractive process, but also the diffractive one. There may be a non-diffractive contribution in the fold pi-zero data as well. In this case, we need to subtract the diffractive contribution for more practical comparison between the perturbative calculation and fold pi-zero result. The diffractive and non-diffractive processes may induce their respective non-zero A sub n for pi-zero production. However, as shown in this figure, since the magnitude of the fold and varifold pi-zero A sub n is comparable, they may share a common underlying production mechanism. But we cannot guarantee because both fold and varifold pi-zero were both inclusively measured. Therefore, in order to understand this issue more precisely, we have started LIG-F star combined analysis using star detectors covering each pseudo-rapidity. It may be possible to identify if the pi-zero event showing non-zero A sub n come from the diffractive or non-diffractive process. If they come from the diffractive process, a rapidity gap should be observed by the star detectors. This figure shows the same LIG-F data points, but this time as a function of PT in different XF ranges. As it was shown in previous pages, we can see the clearly increasing A sub n as a function of PT. The gray field width roughly shows the PT resolution of the pi zero, which is less than 0.025 GB per C. Please note that the resolution of the LIGF detector is much finer than the binning of XF and PT, both XF and PT. The data points were precisely estimated. If we again compare this PT plot with the fold pi01, we can see this orange field gap here between the fold and perifold pi0 data points. It should be reasonable that this gap between two data sets will be the connection from the diffractive to non-diffractive process by studying how comparatively each process contributes to the non-zero A sub n for pi0 production. Both diffractive and non-diffractive processes are expected to be comparably measured in this intermediate kinematic range. So including this physics target, we are planning to operate a follow experiment, the LIGF2, with a new larger detector. For a new detector development, technology of the Alice fold calorimeter, its structure and readout electronics will be transferred. This figure shows a schematic drawing of the Alice fold calorimeter, which is being developed now. With the LIGF2, at first we are planning to measure the varifold pi0A sub n in different collision energy and also a lambda asymmetry as a possible origin of the LIGF result. If you see the right figure, this is the neutron A sub n. Strong atomic number dependence of the neutron A sub n will be also an interesting target of the LIGF2 experiment. As shown in different colors in this figure, the correlation with the BBC shows a non-trivial dependence, which might be connected to either ultra-peripheral collision or diffractive process. Our first operation target is round 24. With the LIGF2 experiment, we hope to successfully explain a kind of physics homework result like this A dependence plot or LIGF result. We will keep updating our new analysis result. Thank you for listening about the LIGF experiment and varifold pi0 result.
Thank you, Minho, for a very nice presentation.
Thank you.
I see Alexei has a question.
Yes, please.
Yeah, hello, Minho. Thank you for a nice presentation. I still struggle a little bit to understand some of the things you mentioned. I think it's a terrific measurement, of course, but the interpretation troubles me a little. So imagine you have, say, diffractive process. Then transverse momentum in this diffractive process would be roughly, what you observe as PT squared, right? And the cross section for diffractive process is actually dropping very quickly in PT. I mean, almost exponentially, and much faster compared to what you expect from twist-free formalism. So at the very beginning, you had an estimate of 75% of non-diffractive processes, while 25% are diffractive. Where do those estimates come from, and how did you manage to give this number of 25 versus 75%?
So do you mean how I identify this 25% diffractive process?
Yeah, exactly. How can you be sure that those contribute as diffractive?
Yes.
What did you use in order to estimate that?
We expect a rapidity gap in diffractive process, as is shown here. And if we use star detectors covering each rapidity coverage, or if we veto, or if we include the detector signal covering each rapidity, then we may identify a rapidity gap. There should be some systematic uncertainty. However, yeah, we are expecting if we use some kind of 4-pi coverage detector location, then yeah, we expect we may identify the diffractive yeah, process. So
Yes.
I'm not sure we will see.
Yeah, definitely. I think it's very important. Still, one needs to have some sort of theoretical expectation, maybe to really estimate what is going to happen actually.
Yeah, thank you for your comment.
Anyone else having any questions or comments for Minho? Okay, I don't see any more hands. If you have further questions, please continue in the chat box. Let us thank Minho one more time. And we move to the next talk, which is by Stefan Diehl.
Shall I stop sharing?
Yes, please stop sharing. I cannot share.
I'm sorry.
Okay, no problem.
Thanks.
Okay, can you see my screen?
Yes, we can see your screen, and please start.
Okay, yes. Hello, everybody. I will talk about the hard-exclusive pi+ electroproduction beam spin asymmetry of the proton in the GPD and TDA regimes. So the first part of my talk will focus on the extraction of the beam spin asymmetry from hard-exclusive pi+ over a wide range of kinematics, which was performed with data from the old glass detector and which was published in PRL last year. And in the second part, I will then do this more precisely with a multidimensional study of pi+ BSA in the GPD regime with the new class 12 data. So let's start with a short introduction. So how can we describe the hard-exclusive pi+ electroproduction? Here, the collinear factorization theorem allows us two descriptions. On the one side, a GPD-based description, which is valid for large Q² and S, and for small T-channel contribution, which means that the meson or the pion is going in the forward region. And then the process can be described by this diagram here, where we have the hard perturbative part of the electron scattering up here, and the soft part is described by a GPD and by a pion distribution amplitude. On the other side, the collinear factorization theorem also allows a TDA-based description based on transition distribution amplitudes, which is also valid at large Q² and S, but this time at a small U-channel contribution, which corresponds to large T-channel values, and which means that the meson is going in the backward region. And in this case, the soft part of the diagram is described by a nucleon to pion TDA and by a nucleon distribution amplitude. So to define our observable of this measurement, we will start with a cross-section, the differential cross-section for a longitudinally polarized beam and an unpolarized target, which you can see here. It consists of different partial cross-section depending on the polarization of the virtual photon. And as you can see, it depends on the angle phi between the electron scattering plane and the hadron production plane, as shown here in the diagram. And the focus of this talk will be on the polarized cross-section sigma LT prime, which is marked with a red circle here. And to extract this part, we use beam spin asymmetries. And to define the beam spin asymmetry, we first write the cross-section in a bit different way by substituting the terms in front of the phi dependence of the cross-section by the three moments, AU cos 2 phi, AU cos phi, and ALU sin phi. And based on this definition, we can nicely define the beam spin asymmetry as the difference of the cross-section with the two helicity state divided by the total cross-section. And this finally gives us this expression here, where we see that the leading term is given by ALU sin phi times sin phi. And this ALU sin phi moment can be directly related to the ratio of the cross-section sigma LT prime over sigma t plus epsilon sigma L, which we also call sigma 0. And how can we now theoretically interpret this quantity? And for this purpose, we look into a GPD-based description, which is valid for T over Q² significantly less than 1. And here we have two models. On the one side, the model from Goldstein, Hernandez, and Liotti from this reference. On the other side, the model from Goloskokov and Kroll, which was published in this reference and which is used for the predictions shown in this presentation. Both models include 8 GPDs, which depend on the polarization of the nucleon and the quark. And there are 4 chiral even GPDs and 4 chiral odd GPDs. And the speciality of the deep exclusive Meson production is the extraction of the chiral odd GPDs, which are very small for classical processes like DVCS. And these chiral odd GPDs contain a lot of physics information. For example, HT is related to the proton's tensor charge, or ET bar is related to the proton's anomalous tensor magnetic moment. And how is this connected to our observable? Here we see our observable ALU sine phi is proportional to sigma LT prime over sigma 0. And sigma LT prime, according to the Goloskokov-Kroll model, can be expressed as a product of chiral odd and chiral even GPDs. And explicitly, we can see that sigma LT prime is proportional to the imaginary part of ET bar times H tilde plus HT times E tilde. And for pi plus, we also know that the chiral odd GPDs are significantly amplified by the pion pole term, which has to be folded or convoluted in each of the GPDs. And therefore, these polarized pi plus observables are very sensitive to the chiral odd GPDs. And when we have a closer look, we can see that ET bar, so the first term, is very small or close to 0 for pi plus due to the quark composition of pi plus. And therefore, we can say that our observable ALU sine phi has a strong sensitivity to this second term, and therefore to the poorly known GPD HT. And this is the goal of the extraction of these studies. So the first studies were done with the alt class detector at JLab, which is shown here as a schematic drawing and as a real picture. And the data was recorded in 2003 when we had a 5.5 GeV longitudinally polarized electron beam interacting with the unpolarized hydrogen target. The electron ID was based on the electromagnetic calorimeter and the Shrenkov counters, and the pion ID was obtained from a time of flight-based maximum likelihood particle selection. And since with class, we only detected the electron and the pi plus, we had to use the missing neutron peak in the E pi plus X missing mass to select exclusive events. And here we can see this missing neutron peak in E pi plus X. One time for the forward direction, which is defined as minus t less than 1.5 GeV square and cosine theta larger than 0 on the left. And on the right for the backward direction, which was defined as minus u less than 2 GeV square and cosine theta less than 0. And as you can see, within our cut borders, which are marked by the blue vertical lines, we get a quite clean signal with only a small background, which can be subtracted from the extracted asymmetries. And after selecting the exclusive events, we can now have a look into the accessible kinematic region. Here we see on the left side the correlation between Q square and W, and on the right side the correlation between Q square and X Bjorken. And the red lines indicate the cuts we place to select the deep inelastic scattering region, W larger 2 and Q square larger 1 GeV square. And we can see with class we were able to access a Q square up to 4.5 GeV square. Then let's come to the beam spin asymmetry. The beam spin asymmetry is defined as 1 over the average beam polarization times the number of counts for positive helicity minus the number of counts with negative helicity in a specific bin divided by the total number of counts in this bin. And when we now have a look on the beam spin asymmetry as a function of phi, one time for the forward direction in the left plot and one time for the backward direction in the right plot, we can see in the forward direction, we get a positive value of ALU sine phi of around 0.08, while in the backward direction, we have a sign flip, and we now get a negative value of minus 0.05 approximately. And to investigate this in more detail, I've looked in different bins in minus t. Here we see different minus t bins starting at very forward angles of 0.11 GeV square up to the backward region of 6.64 GeV square in minus t, which corresponds to small U channel values. And we see in the forward direction at small minus t values, we have a clearly positive sign of ALU sine phi. And this stays positive up to a minus t of 2.34 GeV square. And then we have the sign flip. And here at 3.34 GeV square, we get a clearly negative sign, which stays negative for the complete backward direction. And if we now plot this ALU sine phi value as a function of minus t, we can clearly see this effect, which I already described in the forward region, where the GPD-based description is valid. We have a positive sign, then we get a sign transition at a minus t of around 3 GeV square, which corresponds to the M angle of around 90 degrees. And in the backward regime, where we assume the TDA description to be valid, we have a negative sign. So this is a strong indication for a transition between the two regimes. And we can also look how this behaves for different Q square and X Bjorken values. And therefore, I've plotted ALU sine phi as a function of Q square in the upper row and as a function of X Bjorken in the lower plots, one time for the forward region in the left figures, and one time for the backward region in the right figures. And here we can nicely see for all Q square and all X Bjorken values, we have a positive ALU sine phi in the forward region. And when we go to the backward region, we get a negative ALU sine phi value for all Q square and X Bjorken region values. So this sign transition is independent of Q square and X Bjorken. And as a last part of the talk, I want to focus on the GPD regime and show a comparison to the predictions from the GPD-based model from Goloskokov and Kroll. As we know, this is valid for minus t over Q square significantly less than 1. And therefore, we have to focus on the very forward region for the comparison. And here you can see in the plot ALU sine phi as a function of minus t for the smallest t values. We see the experimental points in black compared to the prediction from the Goloskokov-Kroll model in blue. Now, as you can see, the sign is correctly predicted, but the magnitude of the prediction is too large. And this discrepancy is caused by the interplay between the pion pole term and the poorly known GPD HT, which is a dominant contribution, or the most less constrained contribution to our calculation of ALU sine phi. And therefore, these measurements will help to constrain this GPD HT. But for this figure, I have to mention that the measurement was integrated over Q square and X Bjorken, and therefore we have a quite large uncertainty in the comparison to theory, which is also shown by this large blue band. And to do this more precisely, I did a multidimensional study in the GPD regime with the new class 12 data. So here you can see the new class 12 detector, which is operating in Hall B of JLab since 2018. And the data I'm using for this analysis was recorded during the fall of 2018, where we had a 10.6 GeV electron beam with 86.3% average polarization interacting with the liquid hydrogen target. And I have to mention that the analyzed data is around 50% of what is approved so far. So the future will significantly increase the accuracy of these results. And to do a multidimensional binning, we first have to have a look into the correlation between Q square and X Bjorken, which is shown in the left plot. And here you can see now with class 12, we can access a Q square range up to 11 GeV square, which is significantly larger than the range which we could access with class shown by this red box here. And we then define 9 bins from 1 to 9 in Q square X Bjorken, where 1 is low Q square and X Bjorken, and 9 corresponds to large Q square and X Bjorken values. And for each of these 9 bins, we can now have a look into the T distribution, where we can define 4 to 6 bins in the relevant region for minus T less than 1 or 1.52 GeV square. And we can also clearly see some advantages of class 12 versus class. As I mentioned, we have an increased range in Q square and X Bjorken, and we have significantly higher statistics, which allows us to do this precise multidimensional studies. Then as last slide, let me show you the results. So here we can see the results as black points for the different bins, starting with bin 1 at small q square and small x Bjorken in the lower left edge, up to bin 9 at high q square and high x Bjorken in the upper right edge. And the prediction from the GK model is shown as the blue line. And as you can see, similar to what we had with class, the prediction from the GK model is too large. But what has to be noted is that we can nicely reproduce the slope of the experimental data. Here at low q square, we have some increase and then a decrease at larger t. This is also present in the prediction of the theory, while at large q square, we have a more flat behavior, which is also reproduced by the theory. And I have investigated how we can improve the agreement, and this can be done by increasing HT, as I already mentioned. And when we increase HT by around 1.5 to 2 in the absolute magnitude, then we get a much better agreement. And this is also consistent with observations from other observables and other channels. So this new data will significantly help us to further constrain this so far poorly known GPD HT. So to come to the summary, we have seen that the ALU sin phi moment from the hard exclusive pi plus channel has been extracted for the first time over a large range of kinematics with class. And the results showed a clear sign change from forward to backward angles, which may indicate a transition between the GPD and TDA regime. And I've shown that a high precision study of beam spindle symmetry in the GPD regime has been performed with class 12. And this high precision results will significantly help to further constrain the poorly known GPD HT. Thank you.
Thanks, Stefan. Wagner has a question.
Yes, thank you, Stefan. What about the backward regime for for class 12? Is it difficult to get data?
Yes, this study will come in the future. So far, we are only using the forward detector for the measurement, which can only access the small t region. And once we have completely aligned and calibrated the central detector in the next pass of our cooking, we will also include the backward regime.
Thank you.
Thanks. Any other question? I don't see any more hands, so let us thank Stefan one more time. And let us move to the next talk, which is by Jakub Wagner.
Hello.
Hello.
Do you see my slides now?
Yes, please start.
All right. So I would like to take today to talk about time-like Compton scattering, and especially about what we can learn about time-like Compton scattering from usual DVCS, from usual deeply virtual Compton scattering data, and how we use this close relation between TCS and DVCS to actually predict some TCS observables in a completely model independent way. So this talk is based on work that I've done with my collaborators, which are written below during last few years. Okay, so first thing first, we know that our golden channel for GPD extraction and golden channel for exclusive processes is deeply virtual Compton scattering. This is the deeply virtual Compton scattering depicted here. We can measure it in the electro production of real photon, and we see that we have a highly virtual photon with a space-like virtuality, and this high value of this virtuality allows us to factorize our amplitude to the perturbative part and the non-perturbative part depicted in GPDs. What is TCS? TCS is the very closely connected process, is the process of photoproduction of the lepton pair. And here we have a lepton pair, and here we have a highly virtual photon, but this time with time-like virtuality. And again, the Hard scale given by this lepton pair mass allows us to write the amplitude in terms of perturbative part and the same GPDs as in case of DVCS. So TCS is a very nice process, and I think that it's not. It's worth stressing that we really need to investigate it. It has the same factorization properties as DVCS. It's a great way to check universality of the GPDs because it does not contain any other unperturbative things. Everything are the same GPDs and the perturbatively calculated coefficient functions. It is another great source of knowledge about GPDs because it has different sensitive to different combination of GPDs. In particular, it has a special sensitivity, the real part of GPD H, due to charge asymmetry of the interference term, which I will talk about later. It also is nice laboratory to study the crossing between space-like and time-like processes. So as you see, this process was first proposed almost 20 years ago, but it is nice to talk about it now because this is exciting time and because the new data is coming. And not new data, the first data on TCS is coming. This slide is stolen from PhD thesis of Pierre Chatagnon, which was defended last year in Orsay, and it presents the data, preliminary data, non-published yet from class 12, and we wait, and we are happy that this data will arrive soon. So for example, here we have beam-spin asymmetry in TCS compared to some models, and we have some finally data points to compare to with theory. All right, so our Compton scattering is most conveniently described in terms of so-called Compton form factors. You see here the amplitude for this Compton scattering, and we have Compton form factors introduced here in red, and those Compton form factors are defined as the convolutions, or can be calculated through the collinear factorization as the convolutions of the GPDs and the coefficient functions. And there is very close relation between those Compton form factors in the space-like case of DVCS and time-like case of TCS. At leading order, we see that they are just related by the complex conjugation up to the sign in the axial case. At the next to leading order, the relation is a little bit more complicated. It's not only complex conjugation, but also you have this I pi times this logarithmic derivative of Compton form factor. So you have the same relations for E and E tilde too. So if you know those relations, and if you by accident know Compton form factor from DVCS, you can predict without any modeling and any further assumptions Compton form factors of TCS. And we have such Compton form factors for DVCS, which were fitted using artificial neural networks, using Parton's software not long ago, and they were fitted to the all existing DVCS data that you have depicted here. We have a scan over X and Q square of all the data here, and the cuts that were used to ensure that we are in the regime of the collinear factorization. So what I'm showing now is our Compton form factors for DVCS and for TCS. In the top row, there is a DVCS imaginary and real part for Compton form factor H. So this gray band is the prediction from, not prediction, fit from artificial neural networks. And it's compared to some model prediction of Goloskov-Kroll, calculated with the leading order and next to leading order coefficient functions. So that's the top row. This is a DVCS, and then we are using our relations, so space-like time relations, to predict the Compton form factors for TCS. So this dark band is just a leading order. So we see that this real part on the right-hand side is the same as for DVCS. On the left-hand side, it's just a complex conjugation of what is above. But this wider lighter band is the next to leading order prediction, and it's much wider. And it's wider because it reflects our lack of knowledge of the Q-square dependence. This comes from this logarithmic derivative over Q-square. So here are the Compton predictions for the Compton form factors. And before I go to depict some observables, I need to say something about it. So this timeline Compton scattering is measured in the exclusive production of lepton pair, and we also have other mechanism for production of this lepton pair. This is purely electromagnetic Bethe-Heitler amplitude here, as similarly as for DVCS, and of course our cross section is given by the purely Bethe-Heitler, pure TCS, and the interference term. And to describe this cross section, we need some variables, and one of the important variables is shown here. This is angle phi. This angle phi is the angle between leptonic and hadronic plane, and the other important angle is the angle between outgoing lepton and outgoing proton in the lepton center of mass frame. So this Bethe-Heitler dominates completely when theta is close to 0 or pi. So if we want to measure TCS, we better stay away from theta equals 0 to pi. And this phi is important because this phi tells us about the leptonic plane. And for example, switching this phi to pi minus phi, it exchanges k and k prime. Switching this phi to pi minus phi and theta to pi minus theta. So this interference term is important because Bethe-Heitler is dominating over TCS, especially at not very high energies. At bigger energies, it's a little bit better because of the growth of the gluon and C densities. But at the smaller, but still, the Bethe-Heitler is very big. So we need to find a little bit more differential observables, and this interference term is very nice also because it's sensitive to the real part of H, and it's you see that this interference term here is proportional to cosine phi and times real part of the Compton form factor H. This one is not easy to measure in DVCS. You need a beam charge asymmetry for that, which is not usually easily to access or to measure. And here in TCS, you can use asymmetry between outgoing lepton and anti-lepton, and there were some observable measure defined just for that purpose. And for example, this R ratio, which is just a cosine phi moment of the weighted cross section, that was the observable, which is sensitive to the real part of H. But it's also quite difficult because you have to have a very big acceptance. You have to measure your phi from 0 to pi, basically. So there was another asymmetry introduced recently and defined in the thesis of Pierre Chatagnon, and it was proposed by Mark van der Hagen. And this is this forward-backward asymmetry when you just here compare the cross section at theta phi to cross section and at pi minus theta and pi plus phi. So that corresponds to exchanging lepton to anti-lepton, and that projects out the real part of the Compton form factor H. And here are some prediction by Mark van der Hagen, also taken from this thesis by Pierre Chatagnon. All right, so what are our model independent predictions that I was mentioning? First, let us look at the differential cross section as a function of phi. On the left-hand side, this is a leading order prediction, this darker band, and we see that it's very close to model prediction of Goleskov-Kroll with a leading order coefficient functions, and we also have the next to leading order coefficient functions shown. But on the right-hand side, you see that if you use the next to leading order relation between Compton form factors for DVCS and TCS, then you have a big uncertainty. And that is, of course, very nice information, because it means that just by measuring cross-section, you can learn a lot about Q-square dependence of DVCS Compton form factor. So another observable that we predicted was this R ratio. And for this R ratio, again, we have a leading order prediction with this darker band, and the next to leading order prediction with a lighter band, and some model predictions shown in the dashed and the solid curve. And we see that our next to leading order prediction, again, due to this a lack of knowledge of Q-square dependence, is much less accurate. And then we have predicted also the circular asymmetry. This is also very nice and important observable at TCS, because it is proportional to the imaginary part of H. And we again see on the left-hand side the size of this asymmetry at leading and next to leading order at the typical JLab 12 kinematics as a function of phi.
You have 2 minutes remaining.
Sorry?
You have 2 minutes remaining.
Okay, so I'm heading towards the end now, and so we also predicted the transverse target asymmetry for TCS, which also can be used to measure some different combination of the Compton form factors. And just to summarize a few words about the experimental status of the TCS. So TCS was measured at JLab at 6 GeVs, but unfortunately the kinematical reach was not big enough, and it was very hard to get to the large invariant masses needed to real interpretation in terms of collinear factorization. And also you see here that we really would like for TCS to be above the resonances. So we really need to go higher in this invariant mass square. But we are really excited about the data coming from class 12. And I was mentioning the preliminary results shown by Pierre Chatagnan in his PhD thesis. So we would like also to stress that TCS could be measured in ultra-peripheral collisions, and there are ideas like that. And we can use hadron-hadron or proton nucleus, for example, collisions to measure TCS at LHC or RIC. And last but not least, there are plans to measure TCS at EIC. At Yellow Report, there is some preliminary analysis, and more detailed analysis is underway by Kayleigh Gates and Daria Soken. All right, so here is my summary. So I hope I convinced you that TCS is a mandatory complementary measurement to DVCS and its cleanest way to test universality of GPDs. And it's also a great tool to just extract GPDs and a great independent source of information on GPDs. And we have this nice time-like space-like relation that gives you tools to use the TCS data combined with DVCS to extract the Compton form factors. And we have this special sensitivity to Q-square dependence. And we have presented the first really data-driven and model-free predictions for TCS using just the DVCS data and no modeling. We see that TCS, we know that TCS was measured at JLab at 6 GeV, but there is data from 12 GeV coming, and we could also try to measure it at UPCs in LHC, at EIC, and TCS is part of the Yellow Report. And there's one last remark, that there is a natural extension process which is very similar but different to TCS, when you can replace the final state dileptons by high mass diphoton, like 2 photon with high invariant mass. And that will be described by Oskar Grocholski in presentation, which is 20 minutes from now, basically. Thank you very much.
Thank you, Jakub. The talk is open for questions now. Are there any questions? Please raise your hands. So looks like there are no questions. So thanks, Jakub, one more time.
Thank
And
you.
we move on to the next talk, which is by Witold. Witold, are you here?
Yes, I'm here. Can you hear me?
Yes, I can hear you.
Udostępnij. A nie, to nie to.
Proszę spokojnie.
Co chcesz nic?
Hermetyka.
Nie, to
To?
nie, nic. Tak, to.
To?
To.
Okay. Hermes.
Udostępnij. Okay. Dziękuję.
So we can see your slide. So please.
Thank you. Okay.
Full screen.
Nie. Ja chcę poszerzyć. Poszerzyć to. Dobrze, dziękuję. Teraz zrobimy tutaj view. Zoom
Can
in.
you please repeat full screen?
View. Wait. Okay. Teraz robimy view. Presentation. Okay. All is okay?
I think this is fine. Yeah.
Oh, thank you. So I will start. Title of my presentation is Spin Density Matrix Elements for Exclusive Row Zero. It's for muon, measured muon production at Hermes. It's done for Compass collaboration. So in my presentation, I want to, at the beginning, define spin density matrix element, say something about the experiment, how to select the data, how to determine the exclusive region, and results will be done as a SDME for entire kinematical region. I want to show the dependencies SDME on Q square, PT, and W. I want to say something about the test as general helicity hypothesis. I want to speak about the helicity flip transition, contribution of unnatural parity exchange, and asymmetry natural parity exchange to unnatural parity exchange, and summary. So this is a definition of the spin density matrix element. We used a very well-known Schelling-Wolff representation. In order to do this, it will be calculated photon spin density matrix, and also using the von Neumann formula, we just put the amplitude which describes transition from the initial to final state, which depend on the W, Q square, and PT. This value, if is decomposed for the nine elements, if we want to put the information about the photon. So in the case of from 0 to 3, it's correspond to transverse photon. 4 for the longitudinal, from 5 to 8, it's the interference. When such a separation is impossible, so that just appear the index 0.4. So one of the natural definition of the S-channel helicity is a transition from the photon when we just observe a transition from the photon and vector meson with the say helicity. Something important information is that amplitude, total amplitude, is a sum of the two two amplitude, one which describe natural parity exchange and second which unnatural parity exchange. So see this, for example, in a frame, a Redshift framework, its natural parity is described by J and parity, spin and parity. And if we want to just look for the test for the GPD models and look for the S-channel Helicity violation, we want to observe transition like this. So the photon transverse will be changed for the vector meson for the longitudinal. So we just near the experiment, we use the compass spectrometer, beam of muon, use the muon beam, mu plus and mu minus. Energy of this beam was 160 GeV, with the beam polarization approximately 80. So we use liquid hydrogen target. Was here. You see the two magnet, and the region of the registration of the muon is here. So the next, in order to determine the SDME, we should select exclusive region. So it was done by the several steps. So first we select the events which contains 3 outgoing tracks, mu prime and two hadron with opposite charges, and we just determine the exclusive region by the undetected mass. And we just want to define the region for which we want to observe this. It's a PT, so it's a transfer momentum of the rho, and it was a region from practically from the 0 up to 0.5, and virtuality from 1 to 10 means that we want to observe the hard processes. And W was from 5 to 17 GeV over C. Here, after selection, exclusive region, we will have some not only exclusive region, but also some contribution coming from the semi-inclusive. So you will see here such a analysis when we have the data. After we just want to determine fraction of non-inclusive contribution, and we just define background fraction. So here you see after subtraction, it was presented by the red histogram. So here is going to the 0, and such a sample which we select was like this. So it's practically 50,000 events for our analysis. So in order to have the access for the SDME, we should determine the angular distribution and production plane and decay. So it's necessary classical. We should determine the cosine angle, cosine theta and phi. It was done in the frame of vector meson. And this was also necessary to determine angle between the lepton scattering plane and production plane. So it is, if we determine this, we were able to evaluate 23 SDMEs, 15 will be polarized, and 8 unpolarized. So using for this analysis, we use unbind maximum likelihood. So this is a typical, this is our first result. It's to the entire region. We just put in some order our SDME in a group in the classes A, B, C, D, and T, which corresponds to a different helicity transition. So at the beginning is a S general helicity conservation. So we just have the transmission from longitudinal photon to longitudinal Meson and transverse to transverse. Next it will be interference part, and the third one is a C, where we call it a flip. It's a transition from the transverse photon to longitudinal ρ0 Meson. If will be as general helicity conservation will be only such a transition exists. So all these elements should be equal 0. We see that in the class C we have some elements, in particular R500, which is completely different from 0, and all elements are different from 0. So the elements connected with the polarization is indicated by the green color, shadow green color, and something here on the double flip, and this one is we see nothing. So here is a let's say a dependence of SDME on Q square. It's a group in the same way for the A, B, C, and D. So here is a S general helicity conservation group. Here is a group of B connected with the interference, and this in particular interesting at that moment for us is a C group, and we just move your attention for R500. And we see some dependence on the Q square. It's connected with the class C and class B. So particularly we observe growing element 500 with the Q square. So the same is connected with the relation dependence on PT square. We observe the same growing up with the PT square, A and B, and also R500. And notice that elements from the class D and E just fluctuate near the 0. Quite different situation we have if we observe W dependence. It's a much more stable, it's practically constant, not behave, not increase, not decrease, and also this element C500 is also not changing. So I want to repeat this value from the C, from the class C, 500. You see the same relation, and we just go back in order to want to see if this.
Excuse me, Witold, you have about 3 minutes.
Okay, so this is a relation and described by Grocholski. So it's a definition, and this T0 and T1 is a 500, and here is this described and here in the formula is a GPD's E bar. So it's from the Gross-Kokov-Kroll. Now we just determine also helicity flip helicity flip transition. It was defined. It was defined in this way. So it's a transition defined by the total cross section. So it's observable, very clearly defined this helicity flip transition. We see non-zero and changing with Q square, changing with PT, and not changing with W. And here another spin flip, another class is close to zero. So next we just want to look on the unnatural parity for the rho zero. It's practically zero for this, and for dependence on PT is also close to zero. Next one, if we compare this unnatural parity for the rho zero and for the omega, we see some completely different results. So for the omega is close to 1, here is close to 0, and the same relation is for the dependence on PT and for the W. Next is natural asymmetry for the transition transverse to transverse, and selected by the transition with natural parity and unnatural parity. It's described by these elements from SDME. We see that in the case of the rho zero, the contribution for unnatural parity is close to 0, and this asymmetry is close to 1, opposite to omega, where it is close to 0. So that in the same way, the contribution has the same.
I'm sorry, Witold, your time is up. Okay, we are at the summary. Great.
So it's a summary. It's a summary. We just extract SDME for muon production. We just group on the 5 classes. We show the dependence on the Q square PT. We just observe hypothesis S-channel helicity for the rho is violated. We just see contribution from photon transfer to longitudinal, and we clearly observe dependence on tau 01 on Q square, PT, and W. We have small contribution from unnatural parity is observed at low W, and we just observe unnatural parity to asymmetry, unnatural parity to natural parity, and we notice that dominance is natural parity amplitude. So thank you, that's all.
Thank you, Witold, for a nice presentation. The talk is open for questions. Actually, these online presentations have very little questions. We also saw yesterday. I don't see any raised hands. Maybe there will be questions later, so you can carry that out in the chat box. But let us move. Let us thank Witold one more time, and let us move to the next talk, which is by Oskar.
Hello.
Hello. Could you please share the slides? Okay.
Okay,
So,
you can see my slides.
Yes, we can see your slides. Please start.
Okay, thank you. So in this talk, I want to tell about the NLO description of photoproduction of diphoton with large invariant mass. This is work done in collaboration with Bernard Pir, Paul Schneider, Lech Szymanowski, and Jakub Wagner.
Finished.
First, let me describe the considered kinematics. For this process, we consider interaction of nuclei, which has momentum in z direction, which is struck by a real photon with momentum q in the opposite direction. And at the output, we have the nucleon with momentum p2 and pair of two real photons with momenta k1 and k2 respectively. I will denote by epsilons polarizations of considered photons and by S1 and S2 spins of the nuclei. The whole process will be described in terms of four invariants, which is the mass, the center mass energy squared, which is assumed to be much larger than mass of the nucleon, the momentum transfer squared, the invariant mass of diphoton k1 plus k2 squared, which provides the Hard scale to this process, and also by invariant u prime, which is another Hard scale. And in this process, we have, in fact, two Hard scales, which one of them is m squared, which is a Hard time-like scale, and u prime is, on the other hand, space. So in some sense, we could say that this is something between DVCS and TCS in terms of Hard scales. Why this process? Well, the first reason is that reactions 2 into 3 are new type of processes that can be studied within the framework of UCD collinear factorization with respect to processes of type 2 into 2, like DVCS, TCS, or deeply virtual Meson production. And together with that point, this is probably the simplest of such processes, because we have only real photons in this case, and there are no more complicated contributions like distribution amplitudes, and the whole process at the Born level is purely electromagnetic. Moreover, because of charge conjugation symmetry, for processes with real photons, the amplitude depends only on valence quark GPDs, and there are no contributions from gluons or distributions corresponding to C-quarks. And moreover, there are no contributions from the badly known chiral odd quark distributions at the leading twist, so that we can say that photoproduction of a photon pair is a very clean probe of GPDs. So at the leading order, we apply the factorization so that we split amplitude corresponding to this process into two parts, one being the non-perturbative part depending on generalized parton distributions. And the other part is so-called hard part, which describes the perturbatively calculable interaction of photons with partons taking part in the process. The final form are the amplitudes, is the hard part integrated with the GPD over the parameter x, summed over all possible quark flavors taking part in the process. And at the leading order, we have such a simple three-level diagram. Well, in fact, we have 6 such diagrams corresponding to all possible ways of attaching photons to the quark line. And it turns out that at the leading order, such an amplitude has many interesting features. The first one is that real part of the amplitude at the leading order cancels each other. And moreover, there is a cancellation also of imaginary parts of diagrams, unless the incoming photon is in the middle. That is because of positions of poles of propagators of these two quark lines, because whether it lies on the upper or the lower half of the complex plane depends on whether the leftmost and the rightmost photons are ingoing or outgoing. And for the case when the photon which goes in is leftmost and the rightmost, then there is a counterpart with that photon on the other side, which with the opposite imaginary part. Because of that, the leading order hard part is proportional to sum of two delta functions, so that at the leading QCD order, we have the result that is proportional to GPDs at the diagonal x equal to plus minus psi. Because of that, this is a very interesting probe of GPDs, and we hope that it could be very useful in various GPD extraction programs. However, there is, of course, significant uncertainty to our predictions due to neglecting the NLO contributions that will be discussed later. But for the final part of the leading order analysis, let me present some numerical predictions. The object that we consider here is the differential cross-section unpolarized over m squared t and minus u prime. And leading order results published in Physical Review D show that this process can be studied at intense quasi-real photon beam facilities at JLab or EIC. Let me show an exemplary plot from the site's work. We see that the differential cross-section at some reasonable scales is of order of picobarns times GeV to minus 6, which is small but measurable. In fact, this is of order of contribution from the TCS to the lepton production, at least the pure TCS part, not the integrated one. So this measurable and hence potentially interesting. In our work, we prove that the collinear factorization works also at the next to leading order. We obtain full form of the leading order plus NLO amplitude, and also we make further phenomenological analysis. Let me move back to this picture of factorization with this integral. And at higher orders in QCD, it looks basically the same, but both the hard part and GPD acquire perturbative corrections due to QCD loop diagrams. Of course, there are problems with divergences, so I will work in the dimensional regularization scheme with the number of dimension 4 minus epsilon. The amplitude is written followingly, but with GPD written in terms of finite renormalized GPD plus the correction, which at the first order in alpha strong is the following. Mu f denotes the factorization scale, mu r is the renormalization scale, gamma is the Euler constant, and this proportional to integral of GPD times so-called evolution kernel. And the hard part can be written in the following way, with the leading order contribution and the higher order part, with CQ1 being finite and the divergent term proportional to CQ collinear. If the factorization holds at the one loop level, the divergences from GPDs in the hard part have to cancel each other. To prove it, we need to check whether the collinear part is equal to the following integral of the evolution kernel multiplied by the leading order hard part. If that is true, then the amplitude can be written in terms of all finite quantities. Dependence of on mu r vanishes, and there is only dependence on the factorization scale, which sits in the GPD and term with logarithm. So let us finally move to one loop corrections. We have the following diagrams. There are 48 of them. However, if we consider permutations over photons, then we can reduce this number to 8. Remember that because of charge symmetry, there are no contributions from gluon-initiated processes in this case. The upper 5 diagrams are calculated, let's say, easily as compared to the lower 3. And because of that, I will focus only on the lower part. The 5-point diagram can be expressed in terms of 2 4-point integrals, which are present in the left and right hand side diagram. So we only need to focus on these 2 diagrams. And in that case, calculations are conveniently performed using finite parameterization. We need 3 parameters. And fortunately, we have, as we can see, 3 particles in such diagram, massless and on shell. And because of that, it is possible to find a substitution which factorizes the resulting 3-dimensional integral over finite parameters in terms of redefined ones denoted as U as the following product of
time is up. Could you kindly wind up?
Okay, so we see that it's product of two integrals, and infrared divergences present in these diagrams come only from the red one. The blue one is finite and expressible in terms of logarithm and dilutes. We have analogous cancellations at the leading order. I mean, at the divergent part of NLO, as it was in the case of LO, so that we can obtain the collinear term in a pretty short form. I write it in terms of imaginary part of some expression because it's shorter. When CF is the color factor and C is some constant. And the leading order term is written in terms of...
I'm sorry, Oskar, could you please wind up? Your time is up.
Okay, this is practically the end. If you write it in this term with C being the same constant, you check that indeed there is this cancellation as I said. And to summarize, let me say about the current stage of the work. So we have proved the factorization, and it opens a new class of processes that can be studied within collinear factorization. We have obtained the full form of the NLO amplitudes, also the discussed previously CQ1 term, and the phenomenological analysis is in progress. Shortly, we should have all results implemented in the Parton's framework. Thank you.
Thank you, Oskar, for nice presentation. Are there questions? So I have a question about the slide where you showed the, Charlotte has a question. Let Charlotte ask first.
Yes, hello, I'm sorry, I was a bit late in reacting. I would like to answer, because you said this can be measured at EIC and at JLab. What about the hadron colliders? Is the cross-section too small?
Well, it's small, but we hope that it can be accessible.
Okay. Good.
Oskar, if I may interrupt, I think
Sure.
that the hadron colliders situation is not very good. I think the EIC and JLab are fine,
in case of hadrons,
but LHC is
not good because there is
small.
suppression in S. So, yeah.
So sorry, why is it not very good?
Because in hadron collisions that would come from ultra peripheral collisions, and such processes have the biggest contributions from terms from gluons and sqrts, and they are absent in this case.
Okay, but then if one would, because there are also now fixed target projects at the LHC where they probe the very high X region, would that be a possibility?
I hope so.
Okay, thank you.
Okay, I have a quick question. If you go to the slide where you were showing the two leading order diagrams and the expression of the amplitude below that, I just got a bit puzzled by the expression much before this, the leading order expression of the amplitude. There are two
Leading
diagrams
order,
on the
okay.
slide.
I'm going to the...
Yeah, this one. Yeah, so leading order part is 1 by xi. Is there, okay, so there is no singularity in xi, right?
Yes, you have these singularities at propagators, and because
at
of
xi equal to 0. Is there a singularity at xi equal to 0 for the leading order hard part?
at xi equal to 0, no.
Okay, okay. Okay, thank you.
Okay, thank you.
Let us thank Oskar one more time, and then let us move to the last talk of this session, which is by Wim.
Hello, do you hear me?
Yes, we can hear you.
All right, let me share. All right.
Yes, that's great. Please start.
All right. So thank you. I'm Wim Cosyn, and I'm going to try to give a brief overview, theoretical overview of spectator tagging and DIS measurements. So this is work done in collaboration with Christian Wise, written up for now in these two publications. Especially the second one has a lot of the details of calculations. And if you're interested in that, I won't delve into that here. And I'll also show some results from the JLab LDLD project on these processes. So if you're talking about spectator tagging, we're interested in physics doing light ions. So let me first talk a little bit what the specific physics objectives are using light ions. So one important one for the DIS community, I guess, is neutron structure, right? So this gets you to the flavor decomposition of all the atomic distribution functions. From the nuclear physics viewpoint, it's also interesting because we can use light nuclei to study nuclear interactions and QCD. So you can look at medium modifications, QCD origin of the short range part of the nuclear force, spin phenomena that are specific to nuclear targets that are impossible in the protons. So you have some nuclear gluon effects, for instance. You can also look at coherence and saturation using light nuclei. And if you do coherent scattering, that's not what I'm going to discuss in this talk, but you can do imaging of nuclear bound states, right? In the same way you would do for a proton target. You would image your light nuclei in quark and gluon degrees of freedom, and then you can look at things to make the connection with nuclear physics to look at clustering and nuclei, for instance, how that emerges in quark gluon degrees of freedom. However, in all these processes, it's important to have some sort of a control or at least ID of the nuclear configurations that play a role in these processes. And that's where spectator tagging comes into play. So what you do in spectator tagging is next to some deep inelastic process on your light nucleus, you also detect what we call a spectator nucleon. So this is in the target fragmentation of your light nucleus. And the kinematics of the spectator nucleon, it has a slow momentum relative to the ion center of mass. So this gives you additional control over the initial nuclear configuration. So there's different applications. I'll discuss a few, but the main things we can do is we can actually get to the pole of this propagator by doing an extrapolation of this momentum of your spectator into the unphysical region. Because the deuteron is very loosely bound. I'm now discussing this specifically for the deuteron. It has a very low binding energy, small binding energy. The extrapolation is actually quite small, so it's under control. If you go to a high spectator momenta, then you're actually squeezing your nucleus, and you can look at the, let's say, the configuration dependence. So density, virtuality, dependence of medium modifications. You could also tag something else besides a nucleon, right? Look at things like delta isobars to get an idea about non-nucleonic components inside your light nuclear wave function. This is done at fixed target experiments, for instance, at Jepson Lab, bonus experiments, beach experiment, but it's especially suited for colliders with far forward detectors, because then the spectator nucleon is still moving forward with half of the momentum of your initial nucleus, so it's easier to detect. So I'd like to advertise this talk by Alex Jensch tomorrow morning, who will talk about detailed simulations for the EIC, and I think he will focus on the extraction of unpolarized neutron structure in that talk. So since this is a spin session, I'll talk more about spin dependent observables. So here I'll only discuss the deuteron. So obviously we can extend this to targets like helium-3. It's a bit more complicated. It requires dedicated effort. So that's why we focus on the deuteron for now. It's a licensed nuclear system, so it's loosely bound. I'll discuss effective spin extraction for the neutron, so that will be the double vector spin asymmetry, and also show how we can use the tensor asymmetry, so that's AZZ. I'll introduce it in detail later, to get to the short range part of the nucleon force. We also have first principle calculations of the deuteron wave function, so that makes our theorist's life a bit easier. And as far as spin is concerned, deuteron is spin 1, so if you talk about density matrix, it has 5 additional tensor polarization parameters, and if you look at the deuteron wave function, it has an S and a D wave, right? So this is 2 units of orbital angular momentum. So that gets you additional interesting spin phenomena compared to the nucleon. All right, as far as theoretical formalism, what do we need? So spectator tagging is a case of CIDIS. So it's CIDIS in the target fragmentation region and for a spin 1 target. So I'm going to show you the general structure of this cross section. If we talk about this in the context of QCD, this is talking about fracture functions. So there are factorization theorems for this in the target fragmentation region, so due to Witold, Veneziano, and Collins. So this is all on firm solid basis. As far as the nuclear structure part is concerned, we use light from nuclear structure. So this is natural for high energy reactions on nuclei because there the off-shellness of the nucleons, if you do light from quantization, remains finite. So this is opposite to the instant case. So if you use regular time quantization, your off-shellness becomes divergence in the high energy limits. So we need a dynamical model to express all the structure functions that I'll show you here that appear in the cross section. So first step is an impulse approximation model, so no final state interactions. I'll show results for these observables, and then I'll talk a bit about final state interaction corrections at the end. All right, so the cross section for polarized spin 1 target, the CIDIS case, right? So you detect an additional particle in the final state, has 41 structure functions. So if you look at the unpolarized and then the vector spin polarized case, it's completely identical to the spin 1/2 case. So that's a nice check, of course, but nothing new there. That's everything that people who do TMD physics know inside out, I think, right? So you get all the same structure functions. And I'll focus, so for my neutron spin structure, I'll focus on this structure function, right? Which goes with longitudinal vector, deuteron vector polarization, and electron polarization. Then in the tensor polarization region, there's 33 additional structure functions. So you get a lot of azimuthal dependencies, obviously. And 4 of those survive in the inclusive case. So if you integrate the spectator nucleon, we have 4 that survive, and these are well known since the late 80s, so the so-called B1 to B4 structure functions. And for the tensor case, I'll focus on these 2, so no azimuthal dependence, just let's say the FT-FL equivalent, but then in a tensor polarized region. That's what I'll need for my tensor asymmetry. All right. In terms of how we describe high energy scattering with nuclei, so we have the interplay of 2 scales. On the one hand, there's a deep inelastic process happening, right? So quark is being hit, you have fragmentation, that sort of stuff. On the other hand, there's low energy nuclear structure. And the way we separate those 2 scales is by doing it at a fixed light phone time, because the virtual photon is probing the system at fixed light phone time. So we use light from quantization, like time-ordered perturbation theory, to introduce on-shell nuclear states here and QCD factorization. And then we separate everything. So everything in the EP vertex here is known from high-energy scattering on the proton. And then the nuclear inputs, those things are translated into what are then light from momentum density spectral functions. So all the things we know from low-energy nuclear physics is just formulated differently, because it's at fixed light from time. So this is known from the deuteron, can be extended to other light nuclei, but there are complications there that need to be addressed. So it requires some dedicated effort. So I mean, what to emphasize, this is still low-energy nuclear physics, it's just formulated differently. All right, so if you talk about light front wave function for the deuteron, up to a momentum of V100 MeV, it's dominated by the nucleon-nucleon component. So we evaluate it as a light from quantum mechanics by taking the overlap with on-shell V2 nucleon state. And what you get is a Schrödinger-like equation. So the solution actually looks a lot like your non-relativistic deuteron wave function, but you have a few differences. So you get Mellow's rotations to account for the light front quantization of spin, and your dynamical variable is a bit different. So it's not the relative momentum. You have to light from boost to the rest frame of these 2 nucleon states. So that's what makes it a bit different. All right, so if you then calculate the structure functions that appear in the cross section, so we look at the hadronic tensor, we do the decomposition, so we get to the different structure functions. We get the factorization, so you get the nucleon hadronic tensor, and then some light from densities here. And these actually look a lot like what we would call TMDs for nuclear physics. So they encode how the nucleon is distributed inside this deuteron on the light front, right, with transverse momentum dependence. If you look at the structure functions, it factorizes, so you get some kinematic factor, then some F1, F2 or G1, G2 factor on the nucleon, and then you get a bilinear in the light front S wave and D wave function of your deuteron. It turns out a whole lot of structure functions are zero, so these are sensitive to final state interaction. So it's the same story with chiral optical structures that you get on the nucleon. All right, so applications. First one is the longitudinal asymmetry, so polarized electron, polarized deuteron, and we just take the double spin asymmetry between the +1 and -1 deuteron states here. Denominator is not unpolarized, but it's the summed cross section only including the +1 and -1 polarization state. So we don't need the zero polarization here of the deuteron, which exists. So it's not an unpolarized denominator, but only +1 and -1. And as a consequence, you do have tensor polarization entering the denominator. So it might seem more complicated, but it actually simplifies the theoretical description, as I'll show you next. So if you look at, then we calculate these structure functions in the impulse approximation. If you look at the asymmetry, you have a very nice factorization between a nuclear depolarization factor, which you call D, and then it's just a symmetry on your effective neutron target. Right? And this encodes all the depolarization effects from your nuclear wave function. So that's what I'm focusing on this slide. So this D2 factor, which depends on the kinematics of your spectator, right? So this influences how much depolarization you will have caused by the nuclear structure. And because of the denominator, which only has the + and -1 polarization of the deuteron, it actually has a probabilistic interpretation. So it tells you how much polarized neutrons are inside a +1 polarized deuterons compared to the unpolarized case. So that means it has bounds. It's between -1 and +1. And if you go to 0 transverse momentum for your spectator, you always get 1 because there's no orbital angular momentum, so your D wave cancels out. So it's a pure S wave, your deuteron. So you have a completely polarized neutron inside your deuteron. If you go to high momenta, you see your D wave clearly contributing, right? So that's what you see here. All right, so that obviously gives us an advantage if you do free neutron extrapolation, right? So to the 0 transverse momentum, but then this would be the dashed line here. If you do the on-shell extrapolation, this shows you the effect of the binding energy of the deuteron. You'd have to extrapolate the symmetry here. You see, the symmetries are quite flat, so this should be well behaved at an EIC. So I refer to these publications for more details to that, on that, but it would enable precise measurements of the neutron spin structure over a wide kinematic range. Right, the next is a tensor polarized observable. So here we do need the 0 polarization of the deuteron. So it's this combination in the numerator, and it's completely unpolarized in the denominator. You do not need electron polarization. Tensor polarization only couples to unpolarized electrons, at least in the impulse approximation. And this is bound between -2 and 1, the tensor symmetry. So it has been measured in different ranges of Bjorken X, elastic, quasi-elastic. There's a upcoming Jefferson lab experiments as well. But I'm going to focus on the DIS kinematics, so X smaller than 1, where it's also called B1, right? Referring to the inclusive structure function. But for the tagged case, right? Before I do that, first a bit about AZZ and the inclusive case. So that it's proportional to B1 in the DIS kinematics, which is a leading twist structure function. The QCD operator is the same as the unpolarized F2, so the same evolution. But it encodes the dependence of unpolarized quarks on your deuteron polarization, right? So this is unpolarized quarks and a deuteron polarization 0 minus the polarization 1 case. So it encodes your nuclear effects for unpolarized quark. Because in inclusive DIS, you average over all configurations of your deuteron, you get very small asymmetries. So your denominator is very small. There's only one measurement from Hermes. And interestingly enough, there's a mismatch between normal nuclear theory calculations and the data. There might be some issues with higher twist effect. So this was analysis of the data was done assuming scaling and everything. The Q-squared is quite low here for these data. So maybe there's things like higher twist effects that need to be taken into account. Also, shadowing corrections in the small x region. There are hidden color calculations by Jerry Miller, also including pines, which match the data. So since it's only one measurement, it's not a clear story yet. So JLab will hopefully shed more light on that. What's the advantage of doing this with spectator tagging is since both denominator and denominator are sensitive to unpolarized coordinate distributions, it actually cancels out. So the orthotic factor cancels out, and you only remain with deuteron light from densities.
Wim, your time is up. Could you kindly wind up, please?
Yes, I have. Yeah. So what you get here in the tag case is that you can actually maximize your asymmetry. So to +1 or -2, and you can use this to get to the high momentum part of your deuteron wave function. So that's the physics interest in here. All right, so I have no more time to discuss final state interactions. I do want to mention we have to take them into account. The tagged measurements, there's different kinematic regions. So the shadowing region, intermediate X, high X. I'm happy to talk about this in private if you want to know about this, but I need to conclude. So I showed you we have unique observables with polarized deuterons, so we can extract free neutron spin structure. We can use tensor polarization in the neutron. And we use tensor polarization in the tagged asymmetry to constrain the deuteron D wave, actually. So this is more a nuclear physics application. Final state interactions need to be further quantified in a spin-dependent case, and there's lots of extensions to be explored. Helium-3, exclusive channels, tagged cities, etc. All right, thank you.
Thanks, Wim. So the talk is now open for questions. Any questions for Wim? I don't see any raised hands, but if not now, you can later carry on the discussions in the chat box. So with this, if there are no questions, we close this session now here, and let us thank all the speakers and all the participants for joining and stimulating discussions. Thanks all, and we'll see you after the break.